In this video, we're going to look at the idea of completing the square in a quadratic equation, and we'll look at some connections to other parts of quadratic equations and quadratic functions. So when we're solving a quadratic equation in a single variable, we can do so by using a lot of methods. We have the factoring method, we have a square root property method, we have completing the square, and we have the quadratic formula. This video takes a look at completing the square. If you want to find out how to do these other methods, that is in another video. Now, before we start completing the square, I want to quickly solve this quadratic equation using the square root property. Here we have our quadratic equation set up very nicely as quantity of x minus 2 squared is equal to 36. If I want to use the square root property, all I have to do is take a square root of both sides. However, when I do that, I need to take both the positive and the negative square root of 36. So that would mean that x minus 2 is equal to the positive and negative square root of 36, which is obviously 6. This gives us two equations. One is that x minus 2 is equal to a positive 6. The other is that x minus 2 is equal to a negative 6. And we can solve each. Therefore, this quadratic equation has two solutions. One, which is x is equal to 8 when I add 2 to both sides of the first equation, and the other, which is x is equal to negative 4 when I add 2 to both sides of that second equation. Both of these are solutions to my original quadratic equation. Now we're ready to look at solving a quadratic equation by completing the square. So the ultimate goal of solving using completing the square is to force my equation to look like the previous one, to look like x minus something squared is equal to a number. And then I can take the positive and negative square roots of both sides and then solve using that square root property that we just saw. So how can we do that? Let's jump right into an example of how we use completing the square. All right, so here's what we do. First off, we want to get the x squared and the minus 6x on the same side, but we're going to move this 8 over to the other side. So what we'll do is we'll take x squared minus 6x, and then subtracting 8 from both sides is going to be equal to negative 8. So in other words, we get an equivalent equation of x squared minus 6x is equal to negative 8. Now, what I'm actually trying to do is I'm trying to create either an x minus h quantity squared or an x plus h quantity squared on this left-hand side. And the key thing is that if I were to expand x minus h quantity squared, I'd get x squared minus 2hx plus h squared. And if I did the same thing for x plus h quantity squared, I'd get x squared plus 2hx plus h squared. Therefore, what I'm going to do is I'm going to manipulate this left-hand side so that it looks like x squared minus 2hx plus h squared. Usually what people do is they do that at the same time they fill in the x minus h squared. How do I know what the h is going to be? Well, it has to be half of the coefficient of x based on this expansion. So in my case, we're going to have x minus 3. I have a negative 6 there, so half of that is a minus 3. And then when I square a negative 3, I square 3, I get 9. Therefore, if I add 9 to both sides, I've created a perfect square on the left-hand side. And if I add 9 on the left-hand side, I have to add 9 on the right-hand side to give me a perfect square. That's what we mean by completing the square. I create a perfect square on the left-hand side that matches one of these two forms. And these two forms are the same if we let h be negative. So a lot of people just think of it as this form. X minus 3 squared is this expansion. I added 9 to get that, and so I have to add 9 to both sides. Now I can see that x minus 3 squared is equal to 1. Now I have exactly what I want. I have something squared is equal to a number, so I can take the square root of both sides, taking both the positive and the negative square root of the right-hand side. In this case, that leads to two equations, one of which is x minus 3 is equal to 1, and the other, which is x minus 3 is equal to negative 1. Therefore, this quadratic equation has two solutions. Adding 3 to both sides of the first equation gives me x equals 4. Adding 3 to both sides of the right-hand side gives me x is equal to 2. Those are the two solutions. And if you plug those in, you can confirm that those are two solutions that work. By the way, notice that this expansion is really nice when we have a 1 in front of our x squared. If I don't have a 1 in front of our x squared, I can force it to have 1 by dividing both sides by whatever the coefficient is. And we'll see that in another example. Let's take a look at that other example. Specifically here is example 3. We want to solve this equation, this quadratic equation, via completing the square. If you want to try this on your own, you can. The first step will be dividing both sides by 4, and then we do the same technique we did in example 2. Like I said, the first step is to divide both sides by 4. So I divide both sides by 4, so I get a 1 as the coefficient of x squared. If I had to simplify this, I'd simplify this as well. Another step that you might want to do first, if it's not in this form, is to get all of the x terms on one side, all of the x squared terms on one side. All of the constant terms will eventually go to the other side, but we can divide by 4 first if we want. That's going to give us x squared minus 4.5 times x minus 2.5 is equal to 0. Then what I typically do is I get my constant term on the other side. That becomes x squared minus 4.5 times x. Then I'll leave myself a little bit of space is equal to 2.5. I go back to this and I say I need to add a constant term to make the left-hand side a perfect square. That constant term is going to be h squared. This coefficient of negative 4.5 is going to be 2h. So what people usually do is they say that left-hand side needs to have an h value, which is half of negative 4.5. So if you take 4.5 and divide that by 2, you get 2.25. Therefore, in parentheses, we should have x minus 2.25 on the left-hand side. If I take that number, that's my h. Basically, in this case, the way I've written it, h is a negative 2.25. I need to add on the h squared to this left-hand side and also to maintain balance to the right-hand side. If I take 2.25 squared or negative 2.25 squared, I get 5.0625. That's kind of an ugly decimal, but that's perfectly fine. If I add that to the left, I have to add that to the right as well. You can turn that into a fraction if you'd like. That might be easier to deal with. But in any case, we get quantity x minus 2.5, quantity squared, is equal to 7.5625. By the way, that is the same thing as 121 over 16. So now I can take the square root of both sides, taking both the positive and the negative square root of that 7.5625. If I take the square root of 7.5625, I get 2.75. So let me actually write down all the steps. This is going to give us two equations, as always. X minus 2.25 is equal to 2.75. And then the other equation is x minus 2.25 is equal to the negative of 2.75. When I add 2.25 to both sides, that first equation becomes x is equal to 5. The second equation becomes x is equal to, that would be a negative 0.5. So these two are the solutions for this quadratic equation. Obviously, in certain circumstances, the numbers that you get out aren't nice rational numbers like we did in our case. Sometimes you can get two irrational answers. Sometimes you can get two complex number answers as well. Or sometimes you can get an answer and your second answer is the same thing. But so that's the idea of completing the square. It's forcing this form on one side so that we can use the square root property. And in order to force this form, we force this. Completing the square is not the only way to solve a quadratic equations. You can also use the quadratic formula. Like I said, that's not the topic of this video, but I do want to point out that our quadratic formula says if we have a quadratic equation that's written as ax squared plus bx plus c is equal to 0, then the solutions will be x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Some people would say that is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And you might ask, where did this quadratic formula come from? Well, it turns out it comes from completing the square on this equation right here. So I'm going to show you how that's done in example 4. Solve this equation with an arbitrary value for A, an arbitrary value for B, and an arbitrary value for C when we have this form. Let's go ahead and do that. So first thing I do is divide everything by A. That would give me x squared plus b over a times x plus c over a is equal to 0. Then I'd subtract c over a from both sides, giving me x squared plus b over a times x. And then I'd leave a space is equal to minus c over a, or negative c over a. Now I still have to do the same thing. I need to complete the square. I need to make this left-hand side into a form that looks like x squared plus 2hx plus h squared. That means I am forced to have b over a as twice h. And then I'll figure out what the h squared is to add to both sides. This is going to force my h to be b over 2a. So I get x plus b divided by 2a. That's half of b over a squared. So my h here has to be half of b over a. Half of b over a is b over 2a. If I square that, I get b squared, and then I get 4a squared on the bottom. B squared in the numerator, and then in the denominator, I get 4 times a squared. That's what happens when I square that. And then I do the same. I'd add the same number to the right-hand side as well in order to maintain balance. So this is what we get. I'm going to reorder this just a little bit. This is b squared, I'll say minus b squared over 4a squared minus c over a. By the way, if I wanted to get a common denominator, I'd have to multiply both the top and the bottom by 4, and then multiply the top and the bottom by a factor of a. So that's what I'd get. And now I can combine this into one single fraction. Let me go ahead and do that quick. This single fraction, excuse me, would be b squared minus 4ac all divided by 4a squared. Now I can take a square root of both sides. When I take a square root of both sides, I have to make sure that I take both the positive and the negative square root. So I get square root of b squared minus 4ac, all divided by 4a squared. Well, the square root of b squared minus 4ac is just the square root of b squared minus 4ac. But I can take a square root of the denominator, and when I take a square root of the denominator, the square root of 4 is 2, the square root of a squared is a. Excuse me. So I end up with either the positive or the negative of the square root of b squared minus 4ac, all divided by 2a. And then you can see what's going to happen. I'm going to subtract b over 2a from both sides. That gives me x is equal to negative b over 2a plus or minus this expression, this square root divided by 2a. Combining that into a single fraction gives exactly what we are looking for. X is equal to, since they have common denominator of 2a, x is equal to opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So this shows you that the quadratic formula is just coming from completing the square on this general quadratic equation. Ax squared plus bx plus c is equal to 0. So that general quadratic equation, when I complete the square, leads me to the quadratic formula. So that's one really interesting connection between that quadratic formula and completing the square. Another interesting connection with completing the square is the idea of the quadratic equation and finding the vertex of a quadratic equation where we have this general form of y equals ax squared plus bx plus c. Now, if I have the standard form of a quadratic equation in two variables, then it's the transformation of y equals a times quantity x minus h squared plus k. And it's really easy to see what the vertex is in this case because of the transformations from our base y equals x squared. We've moved that h units in the x direction and k units in the y direction. Therefore, the vertex in this standard form is h comma k. We don't right now know, well, we do know, but it's not given to us what the vertex is in this general form. But if we rewrite this general form into this standard form, I could figure out what the h would have to be, and that would give me the x value of my vertex using completing the square. So let's go ahead and do that. Let's take this general form, y equals ax squared plus bx plus c, and let's rewrite it into standard form of y equals a times the quantity x minus h squared plus k. All right, I've written the first couple of steps um, to doing that. So I start with my general form y equals ax squared plus bx plus c, and then I divide both sides by a. So when I do that, y over a is the term on the left, x squared is the first term on the right, b over ax is the second term on the right, and then c over a is the third term. Then I would subtract this constant of c over a from both sides. If I do that, my right-hand side becomes x squared plus b over ax, and my left-hand side becomes y over a minus c over a. Now I want to complete the square on this right-hand side. So I need a number in here that will match up with x minus something squared. The something has to be half the coefficient. So we have b over a right now. Half of that is b over 2a. When I square that, it means I need to add b squared over 4a squared onto the right. In order to maintain balance, I would also have to add b squared over 4a squared on the left. That gives me the equation y over a minus c over a plus b squared over 4a squared is equal to x minus b over 2a squared. Now I can actually stop right now if I just want to know the x value this of the vertex, because I know the parentheses is going to look like x plus b over 2a. My standard form has x minus h in parentheses. So, whoops. So I know that my value of h has to be the negative of b over 2a. That means the x value of a vertex in this of the vertex of this parabola has to have value opposite of b over 2a. Now, if you want to, you can rewrite this by doing a couple of things. I'm going to multiply both sides by a to begin with. That'll give me y minus c plus b squared over 4a to the first power is equal to a times x plus b over 2a, quantity squared. And then I can add c and subtract b squared over 4a to both sides to give me the actual form that I'm looking for. Y equals a times the quantity x plus b over 2a, that quantity being squared, and then plus c minus b squared over 4a. So now I can see that the x value has to be opposite of b over 2a, the x value of my vertex. I can also see that the y value is going to be this thing, which usually isn't worth memorizing. Usually we just find the x value of the vertex and then plug it in to find the y value in practical cases. But there you go. That's what it is. Hopefully that all makes sense. Basically, this shows you that the x value of the vertex is the opposite of b over 2a. So completing the square does that. Um, it says that if I have my equation, my quadratic equation in two variables that's written in this form, then the vertex has x value of x equals negative b over 2a. By the way, this equation of x equals negative b over 2a, that is also the equation of the axis of symmetry for the parabola as well, because the axis of symmetry is the vertical line that goes through the vertex. But vertex has x value, x equals opposite of b over 2a. We saw that using completing the square. In my class, I don't do a lot of completing the square problems, but it is nice to know, and it's nice to be able to have in your toolkit. So that's the end of this video. Hopefully you saw how to solve quadratics using completing the square, and how completing the square leads to a couple of the things we saw in previous videos.